Hello everyone. Today we are going to talk about the 2016 DenseNet, Densely Connected Convolutional Network, and this is also the best paper from 2017 CVPR. The author are the folks here, and again, this is my personal reading note. What I'm trying to achieve is bring you a high-level summary for the DenseNet paper. And just one reminder, in this paper, there's a lot of comparisons between DenseNet and ResNet. So it would be good that you have some fundamental understanding of the ResNet. I will also put my ResNet video on the description below. So the problem of what DenseNet trying to solve is actually inside the ResNet. The DenseNet author argued that the element-wise conditions, which is called the summation here, is actually impeded the information flow inside the network. So you can see that this formula is the ResNet paper. So you have the feature maps and you do the transformation functions, and then you have this shortcut connection. You can add them together with element-wise addition, which is the whole summations operation here. And this is actually arguing by the DenseNet papers that you shouldn't do this. So what is the proposal from the DenseNet is actually a different architecture. And this architecture you can see compared to the conventional one, you have a more extreme shortcut connections. You basically connect all the layers to each other. So if you have L layers, total L numbers of layers, how many connection you have, you can use this formula to describe that. And the important things of the DenseNet paper is actually tell you a few things, right? The first is the different architectures, which is very state of the art during that times. You only have this conventional convolutional patterns during 2016, right? And this paper proposed this kind of totally extreme shortcut connection patterns. And the second thing is it bring up the concept of the feature reuse. And the third thing is personally, I think is the most important thing. Maybe I'm wrong, but I feel this concatenation concept is actually brings impact a lot of the paper afterwards. If you see the 2020 YOLO V4 papers, it actually modify a lot of the concept from the concatenation instead of using element-wise addition anymore. So we'll also focus on what is the difference between this summation and concatenation here. So the advantage for the DenseNet papers is the first thing is alleviate the vanish gradient problem. The second thing is to strengthen the feature propagations and strong gradient flow. Later we'll talk about that. And the third is it encourages the feature reuse. The fourth thing is actually a little bit counterintuitive, is it actually reduces the number of parameters. Later we will talk about why. So the first point, right? This is exactly the same as the ResNet. If you have the shortcut connections, you basically have easier gradient flow, and that the second point and the second point and the first point are combined together is that they actually benefit from those shortcut connections. And of course, the DenseNet has more intense shortcut connections that will even strengthen the propagation, the feature propagation, and also the gradient vanish problem will be solved. And not completely solved, but it's really greatly help to mitigate the gradient vanish problem. So later we'll talk about more on the third part and the fourth part. But again, I just want to show the picture here. If you have your arrow signals and you have such a dense connections, then your backprop can directly prop to the early layer instead of the conventional one. You want to backprop one layer after the others. So this error message, which will change the weights for your network, can actually more efficiently propagate to the early layers. And that is why the feature propagation and gradient flow is strong inside the DenseNet. It's very intuitive. And this diagram here is a little bit overwhelming with information. Let me try to walk through that. So there's a one thing, very important thing is the concatenations. And how does the DenseNet paper doing things is actually, let me try to walk you through. You have the input feature map, and after you do um, transformation functions, you will have the output of a certain number of the feature map output, right? You can have a three. Let's talk about only the channel number now. You have a channel of 3 comes in, and you can have a channel of, let's say, 10 as output, right? And after you have this channel of 10 as an output, what you need to do is you need to take your input, the original 3, concatenate them together. So now will be 10 plus 3 will be 13. So you can basically decide how many output you will always have, right? You can always have 10 as output. So you can take this 13 feature maps and you can do a transformation functions to generate this red thing. If let's say if it's a 10 here, then you're gonna take your 13 concatenate them together. So that will be 10 plus 13. That will be 23 feature maps now. So this patterns is what what is used inside the DenseNet, and that numbers I'm talking about all the time. If you want to generate 10, that is it called growth rate. So means that every layers you increase in 10, and then you concatenate from the original one, and you increase in 10, you concatenate the original one. So actually your feature maps number is increasing slowly, right? It's only 10 after each other. If you think about the conventional CNN, usually sometimes it's like 128, 256, and then suddenly jump to 500 something. So it's doubling super fast comparing to this slow growth rate. So that is one of the reason why the parameters can be reduced, because actually your depth information is not that much compared to the conventional one. However, it always depends on how many layers you will have. If you have 1000 layers and always using that patterns, of course you will have a huge problem. But that is not the architectures will be inside DenseNet. Later we'll talk about that. I just want you to understand the pattern here is actually you take your feature maps and then you do a transformation function and you generate here, let's say 12, or we use our original example is a 10 here, and then you take all of this input and concatenate here, and that is the final result. So this is how the feature map size is growing after each other. So that's this growth rate, you can define the number here. So what is actually happens between here to here? Let's say is you can check. Let's check first this pictures here. So what you have is actually you take the input feature maps and you go through this pattern is already pretty default during the times, right? And even now, right, you do a batch norm first, and then you do a activation functions. In this case, is ReLU, and then you pass another convolutions to generate this output. So this is actually happens between here and here. But what you can do more is actually add another bottleneck layers here. But what is the reason why we want to add these bottleneck layers is very intuitive. Every time you see this bottleneck layers or you see this one-on-one convolution, you always need to think about, okay, they want to do something for this depth, for this channel-wise numbers, right? Because we already talked about before, if you have a lot of layers, then the final numbers of this depth will be super huge. Let's say maybe 1000, and you don't want that much feature maps. So what you can do is instead of having 1000, you can use one-on-one convolutions to change the depth information to make sure you can reduce the parameters, and then you can do another this standard way of batch norm, ReLU, and convolution to generate this output, the K channels here. So let's see again. If you have L layers, and every layers you will increase k of them because the k is your growth rate, right? So in total you have L times k numbers of channels, And instead of taking all of them to compute the convolution 3 to 3 convolution like this case, instead of doing that, you add another bottleneck layers in between, try to reduce the numbers of the channel size. In this case, become 4 times k. So from L to 4. Let's say if L is 1000, right? Now you reduce how much you reduce 250 times, and then you always generate the k, because k is your growth rate, because now you are in the L plus 1 layers, right? Then what you need to do is take your input, concatenate them together to form this. So this is how the patterns are doing there, and you're probably wondering why you're doing this concatenation, why you're doing this um, the growth rate like that. Later we're trying to talk about the intuitive. Just wait for a few slides. So again, in this slides I just want to tell you that to reduce the number of parameters, it's probably not that intuitive. But if you think of the channel size, right? The channel size, what we talked about before, is just like increasing 12 and increase another 12. But in the ResNet or conventional ResNet architecture, you probably will jump from the 256 and then 512 and then 1024 and then 2048. So the increasing is like super huge. So by doing this slow growth rate, you can control the number of channel feature map size in this case to grow slowly. And also you can do something in between, is what we talked about before. The bottleneck layers, you can use bottleneck layers to make sure your computation is actually reduced a bit. And then you can use the formula to calculate the parameters, right? In this case, the ResNet connectivities, you have the input size. Let's say you have a C number of C as a channel size number. And then what you're doing here is you will do a convolution, and the convolution go through all of them. So that would be a C. And then you need to have a C times number of convolution, right? If you go one feature maps, go through all of them, you will generate one output, and then you have C numbers of filters, so you will generate in total C here. So the total computation is C times C. And in that case, if it's a dense net, that will be L times K, and then the output will be K, right? Because this is just the number of features you need. After another layer is just growth rate will be K. So from L times K, the output will be K. Of course, you do concatenation, but concatenation you don't waste computation, right? So the number of computation is L times K times K. However, remember that the C is really big, the K is really small. Usually C is like 1024, 256, but the K is like 12. So that's how much reduction you have in terms of parameters. Just want you to have the intuitive understanding of why it's talking about. You probably intuitively feels that this kind of concatenation pattern will introduce a lot of parameters, but it's not true. It's actually saving the parameters, reduce parameters. And now what I at the beginning what I think personally I think is the most important concept of this paper is actually the concatenations. And we also talked about before the ResNet is using summation. So I really like this reply. Um, that saying that the summation of the tensor are the signature of the ResNet, and concatenations of tensors are first used in inceptions. It's another architecture, right? And later in DenseNet. So the DenseNet concatenation feature maps of the previous layer similar to inception eight, so that the next layer can choose. This is very important. The next layer can choose to work on either the feature maps generated by the immediate earlier layers, or it can work on the feature maps that the convolution operations before the in, intermediate earlier layers. What does it mean is if you think of the conventional um, convolutional operations, right? If you think of the conventional operations, what it does is actually you have this number of feature maps. And in order to generate the next layer of the feature maps, you need to go through all of them. And then you probably collect in some informations through all these feature maps. And then you generate one output. Then you're gonna take another feature filters and to go through all of them, and you generate another of them, right? And you do that like C times to have this. But in the DenseNet, you have your feature maps, and then you generate output. But instead of toss that away, I take you with me, I put you here, and the next layers, right? This one, you're gonna take all of this and generate an output. But the original feature maps is attached here, whether you want to use, whether this will provide a useful information for you, you can decide that by yourself. During the fashion of backpropagation, right? You have the magic happening there. You're trying to find the loss, uh, the minimize the loss functions, right? That's using some imaginary example. We all know that the lower part has the like semantic weak semantic um, informations, right? For example, like curves, the age, this information. But in the higher layers that you have what you have like a strong semantic information, like you have the human face, for example. And then you can choose, as during the convolution process, you can choose, do you want a high information or do you want a low information? For me, this is kind of like FPN. Yeah, if you don't understand FPN, you can check my the other video. But for me, this is like a FPN. You can choose what kind of level of semantic information you need, and then during your um, convolutional process, you can go through all these feature maps and to make sure which information you need. I hope this is kind of provide you information. In the next slides, there will be some um, picture of that, but let's try to walk through this one first. So the feature reuse is very important things inside the DenseNet. As I said before, you always take the previous feature and you concatenate with you all the times. And so you make sure your feature is always there. But inside the RESTnet, instead of doing that, right, you actually add them together. And when you add them together, they become correlated. So let's say if you have the edge information and if you have the human face information, and now you suddenly add them together, they are correlated to each other. Oh, of course, you have blending those information together, but it's hard for you to separate them and they become correlated to each other. And this is something you want to make sure they are clear, separated, they are diversified, and then you can always choose which kind of information you want to have inside those feature maps here. Basically, this is um, a, a intuitive way of explaining this. And if you see here, right, this is what I'm saying, like FPN concept. Let's say the stars means how many high level information you have. We always know that the higher, the later the convolutional layer is, the feature maps is you capture a higher level informations like a human face, and this might be the edges of your eye, and then this might be the structure of your nose, things like that. So you actually combine all of them together, concatenate, because each time you concatenate them each other, so the final output is just you take all those information and you send them to the classifier or detector. Then you have more um, rich information because you combine all of them. You just you take all the features maps with you. You don't add them together, you don't correlate them together. Instead, you put it there. Whether you want to use is your choice, right? So it turns out that it generate a smoother decision boundary, and also it works well on insufficient training data. It's just a surprise the output of the DenseNet architectures will create in this. And now I just want to step back. We jump out and let's have a bigger picture of what is actually happening inside the DenseNet, right? So we have this dense architecture we're talking about before. We are all talking about only this tiny corner here. So it's not always like a infinity connected them to each other. This is called dense block. Only inside this dense block, you're doing these crazy connections. And after the dense block, you have these transition layers. And this transition layer is actually doing a convolution and pooling here. I will explain why. So the pattern is like that: dense block, transition layer, dense block, transition layer, and following by that. Why? Is because when you think of the dense block, in order to connect them, in order to concatenate them to each other, you cannot reduce the dimensions, right? Because you want to concatenate all the feature maps together. So how can you reduce the dimensions? I mean, the dimension in this case, I mean the width and the height of your image, of your feature maps, because you always changing the depth here, right? You increase the depth along the way, but you don't change any of your width and height. That is why you need a transition layer, which is using the pooling to reduce the resolution of your feature map here. So that's pretty intuitive. You need a dense block to increasing your feature map's channel size, but along the way you need something to reduce the resolution of your width and your height. And that is actually happens inside the transition layer. So so now we jump back again into that dense block. Okay, another way I really like this description here is it's called a collective knowledge. Um, so this is probably another way you can look into the problem of concatenations, right? You have the feature map and you can take that always with you. And whether you want to use that is your choice. And along the way, right, you have this global state. This is your global state now. And based on this global state, I do some convolution operation and I generate another k layers because that's my growth rate. Every layers I will generate more k layer. And this k layer is actually learning from those things. And it learns from those things and generate a um, like the essential informations of from those feature maps, right? And then you add on top of that your previous information. So by doing that, you learn something more and you take all your previous knowledge with you and you learn something more and you take all your previous knowledge with you. So this is like a collective knowledge along the way, along this path. You are growing your knowledge for your specific problems, and then you try to make sure that all these tiny layers increasing, you don't lose any information before. But if you do the summations, right, you correlate them to each other, and you cannot tell the efficiency or how well you learned is actually combine each other. That's kind of the intuitive inside this concatenation all the time. I hope I provide you some basic understanding of this concatenation. Personally, I think that's the most important concept. And let's have a look. The architecture here is basically the same as ResNet, right? You have the 224 as input size, and you come in with some you first doing the convolutions and pooling to reduce the dimensions, and you go inside your dense block, and you see when you go inside your dense block, your um, 2D information is not changed. 2D here I means the resolution, the width and height. And always after the transition layers, you reduce your resolutions because you have a pooling layer here. And then along the way, you're doing these things, and you see it's a transition between dense block, transition layer, dense block, and inside this dense block, you know all the magic happening there. It's this crazy connections, and it's this collective knowledge try to combine the features and reuse those features and concatenate them together and to generate the output. And what is the magic happen also here is this growth rate, this growing the number of your layers, and you try to make sure that you are not using too much computation. That is why you have also the bottleneck layer there. So this is the performance output. Basically, you can see the DenseNet here. The K is the growth rate, right? This is inside the dense block. Each layers you will increase 12 of your feature size. And if you see the B here means the bottleneck layers. This is those one-on-one convolution layers you want to use. And this C is a compression, so you can have additional compression in terms of your channel size because probably you have too much um, dense layers, so you increase too much of your feature map, um, the channel size information, so you can use another compressions. You just a multiplier, you can compress your architectures further. So this is my final slides. That just want to tell you, if you're using the DenseNet within uh, the technique of bottleneck layers and compress of the channel size, you can actually achieve the same error rate compared to the ResNet. The red is the ResNet here, but with the 3 times fewer parameters. So you can achieve the same um, performance. And that is really state-of-the-art performance because of using those techniques together. The first is this dense block. Inside this dense block, there is this crazy architecture connected to each other. Let's jump back here. This crazy architecture connected to each other. And inside this architectures, what is happening is actually reuse the concatenation of reuse those features informations and to make sure that they are efficient to be learned, and also you can reduce a lot of the parameters by this small number of growing rate. And these bottleneck layers can be happening in between to make sure that you reduce computation because you change this channel size. And then during this transition, during the transition here, you can actually have a multiplier to compress them to make sure your channel informations can be even reduced, or you can also compress inside your dense block there. So that's the B and C meaning here. I hope I convey the high level understanding of the DenseNet. This is in the future, if you see any concatenation patterns, you can always refer back to the concept of DenseNet to understand that it's using the feature reuse, is trying to make sure that you take all this collective information with you, and then to have a better understanding of the whole problem. Thank you.